The first evidence of nuclear fission was observed in the late 1930s by two German scientists, Otto Hahn and Fritz Strassmann. In their experiment to study the effect of firing neutrons at some uranium compounds, they discovered that the uranium nucleus had split into two fragments of about equal masses. The interpretation of this discovery as a fission reaction was worked out together with Lise Meitner and Otto Fritsch. Further experiments showed that uranium-235 fission yielded an enormous amount of energy, and each fission also yielded at least 2 neutrons. From this, they realized that a chain reaction would be possible with an unprecedented energy yield. The initial step in a typical fission reaction occurs when a slow neutron, also called thermal neutron, is absorbed by a uranium-235 nucleus. This increases the mass number of the nucleus by 1, producing a uranium-236 nucleus which is in an excited state. The uranium-236 nucleus is highly unstable and splits into two fragments almost instantaneously. In addition, some neutrons are also released. Click the play button to observe the animation of the nuclear fission of uranium-235. However, the animation should not be taken too literally. Click the sequence button to reveal the sequence of a fission reaction. Click the equation button to reveal the equation for this fission reaction. Note that the fission reaction involving uranium-235 splitting into krypton and barium is not unique. Other outcomes are also possible. Click the Other Possible Outcomes button. Fission resulting from neutron absorption is called induced fission. Some nuclides can also undergo spontaneous fission without initial neutron absorption, but this is quite rare. In a nuclear fusion reaction, two or more light nuclides come together or fuse to form a larger nuclide and energy is released. Click the play button to see the deuterium-tritium fusion reaction. Click the equation button to see the equation of the deuterium-tritium fusion reaction. When a deuterium nucleus and a tritium nucleus fuse, a helium nucleus and a neutron are formed. The difference in the total mass of the initial nuclides and the total mass of the final products is transformed into energy. This reaction yields 17.6 MeV of energy, but requires a temperature of approximately 40 million kelvins to overcome the Coulomb barrier, the repulsion caused by the positive charges. Summary. In nuclear fission, a large nucleus splits into two nuclides of almost equal size with emission of neutrons and energy. Fission resulting from neutron absorption is called induced fission. Some nuclides can undergo spontaneous fission without initial neutron absorption. In a nuclear fusion reaction, two or more light nuclides come together or fuse to form a larger nucleus.